Assalamu alaikum. In the last class, we have derived the expression for equations of motion. In this video, we'll derive equations of motion for an object moving under gravity. Let's do it. Now, before going ahead, let me write equations of motion, which is otherwise known as kinematic equations. First equation of motion, which relates the velocity at a time, is written as v is equal to u plus at. Then the second equation of motion is given as s equals to ut plus half at square, and a third equation of motion is given as v square equals to u square plus 2a s. Now, these are equations of motion for an object moving in a straight line. Already I have told you we cannot apply these kinematic equations for objects moving either in a circular path or under a oscillatory motion. For both the cases, we cannot apply these equations. It is especially used for object moving in a straight line. Remember that. Now here, I consider an object whose mass is equal to m. I consider an object whose mass is m, moving only under the action of gravity. Only under the action of gravity. Here g is acceleration due to gravity. Acceleration due to gravity. What is this acceleration due to gravity? So suppose if you drop an object from certain height from the earth, the object at present, when you are holding the object in your hand, it will be at rest. So the velocity is 0. The moment you leave it, it starts moving towards the earth. This is due to the presence of gravitational force. Now, due to this gravitational force, the speed or the velocity of the object increases. Whenever there is a change in the velocity, we call it as acceleration. Now, in the last class, I have told you about it. If this acceleration is due to gravitational force, then we call it as acceleration due to gravity. It represented by letter g. On the surface of Earth, its value is nothing but 9.8 meter per square second. This you might have learned in lower class. Now let's go ahead. Here I have an object. Let us consider this one as an object whose mass is represented by letter m. Now, first it is thrown from a certain height. For my convenience, the motion of this object is represented by a coordinate system in which I take a y-axis in the downward direction. Positive y-axis is taken in a downward direction. Now, in general, it is taken as x-axis and the y-axis is taken in the upward direction. But here, for my convenience, to make my work easy, I have taken y-axis in the downward direction. So it represents positive y-axis. Let's see. Then, few more assumptions I do. I told you here the acceleration is only due to gravity. Okay, and here I assume that the presence of air resistance is nil. Now I neglect the presence of air resistance. So whenever an object falls only under the influence of gravity in the absence of air resistance, then we call such motion as free fall. You remember this. We call such motion as free fall. So what is the condition? Condition is that the object should move only under the action of gravity and the air resistance must be 0. Clear? Now, case 1, I'll start with case 1. I say that there is an object which is thrown with a certain velocity u. And u is taken as initial velocity. Initial velocity. Now, when it is thrown from certain height, displacement covered by the object to reach the ground is the represented letter y. Okay, the next, what be the acceleration attained by that object? Let me write that one here. Here the acceleration, I told you earlier, it is a, being a vector quantity. I use this symbol. A vector is taken as g, acceleration due to gravity. Okay, and here the object is found to be moving along y-axis. We know the unit vector, orthogonal unit vector which is acting along y-axis is nothing but j cap. Okay, so to provide a direction to g, I am going to multiply this with unit vector which is nothing but j cap acting along y-axis. Understand? So j cap. Now in our previous class we have learned about a resolution of vectors into various components. So that I am going to use here. I am going to resolve a vector into its components. Resolving a vector into its components. What I will get if I do so? Let's see. A vector is written as ax acting along x-axis. So the unit vector along x-axis is nothing but I cap plus the component of a vector along y-axis is ay. Unit vector is j cap plus the component of a vector along z-axis is a z, and here the unit vector is k cap. So this is what we have, and I have told you earlier, here a vector is nothing but j cap that I use here from this equation. Okay, so what I'll get will become equal to j cap. Fine. Now I'm going to compare these two parts. These two things I'm going to compare. On comparison, see what I get. On this side I have got only one unit vector, that is a j cap acting along the y-axis. Here I have got three components. This is the component of a vector acting along x-axis. This is the component of y vector acting along this is the component of a vector acting along y-axis. This is the component of a vector acting along z-axis. Got it? Now on comparison, I'm comparing the components. See what I get if I do so. To save the space, I write it here. In this side, Ax I cap is present. This side there is nothing. So Ax I cap is taken as 0. Fine. The next here we have Ay j cap. Before writing here, I'll do one thing. I'll take this part Az k cap. Why am I doing so? You will come to know later. This side we do not have anything with the k cap, so it is 0. Understand? Next, I have a y j cap. Here, the term which is multiplied with j cap is nothing but g. So I write it g j cap. Now I'll do one thing. For better understanding, I'm going to include the remaining terms, remaining components. What is that? As for the component of acceleration along x axis is nothing, so taken as 0 I cap plus here the component of acceleration along the z axis is again 0, so 0 k cap. Now I hope this might be easy for you to understand. I have compared this to obtain 0. I compared this to, I got g. I compared this to and got this one. Fine. If you want, you can mention these things here. Now we know very well when we multiply 0 with anything, the value obtained is nothing but 0. Now this I take. Okay, here this and this will cancel, and what we obtain is nothing but this. Ay is equal to g. Understand? Which is otherwise represented as a. Okay, so acceleration is nothing but g, the acceleration due to gravity. I box this for better visibility. I got the value of yes, I got the value of a. Then I am going to substitute in these three equations to get the kinematic equations of motion or kinematic equations for an object moving under gravity. Okay, let's do it. I will use these things here. Okay, substituting the value of yes, a and the above equation. What I'll get first. First equation of motion, which provides us velocity with which the object is under motion. V is equal to initial velocity is u. It's taken as such. The place of a. Now what I get? I have to write g. Fine. T is written as such. And second, that is equation number 1. Then second thing here. What is this? In the place of yes, I have to mention this value. So this will become, see this one, y equals to ut plus half. The place of a, I have to write a g. G t square. This I take as equation number 2. Fine. Now let me write this one here. To save the space I am doing so. Now this one here. Square of the speed or the square of velocity with which the object is under motion is obtained using this equation of motion. V square. The final velocity is equal to initial velocity, square of initial velocity, plus in the place of E I write a G, in the place of S I have to write a Y. Fine. This is equation number 3. This is equation number 3. So we have got 3 equations of motion which represents the motion of an object towards the ground. Here when I say that object is under motion, it means that the object is kept very close to the ground. Okay. The next this is the case 1. The case 2. Now, before going ahead, the certain changes I do want to make to this one. Now, I take this case 1 as this case 1. I slightly modify this. This case 1 represents the falling of an object. From height h. Suppose the object placed at one point which is at height h from the ground surface. It is so. We have to make certain changes to these 3 equations. The first equation will remain as such. First equation remains as residual plus gt. First equation of motion. What is the second equation of motion? Second equation of motion. In the place of y, I take a h. What I do here? Y is taken as h. So second equation of motion, h equals to ut. Now let's change the color. H is equal to ut plus half ut square. This is taken as equation number 4. Now for convenience, the next we have y. Now which I am going to replace with the h. That's equation number 3. That is the third equation of motion. As well as v square is equal to u square plus 2gh. Let's take as equation number 5. Here equation number 1, 4 and 5 represents kinematic equations of motion for an object under free fall from height h from height h towards the ground. Got it? Now next we'll discuss second case. Case 2. Here I consider that the object is thrown. The first case we have thrown the object with some initial velocity. In the second case, I consider that the object is dropped from certain height, say h. So initially when the object is kept at certain height h, the velocity of that object is 0. Initial velocity is taken as 0 in such case. Object whose mass is m from height h. Now, the initial velocity. When the object is not dropped, no, when someone is holding it in their hand at that particular moment, the initial velocity is considered as 0. It doesn't possess anything, it is at rest, isn't it? When the object is at rest, when the object is at rest. The object is at rest, the velocity of the object is taken as 0. Now, the moment it is dropped, it starts moving towards the ground. Now, slowly due to gravity, its velocity increases. Now, after some time, after time t equals to capital T, after time capital T, it attains velocity v. Here v is the final velocity when the object has hit at the ground. Velocity. Okay. Now I am going to modify these three equations, equation 1, 4 and 5, according to this case, according to new assumptions. Here, equation number 1. Equation 1 is written as what I do? I take it as v is equal to u plus gp. Now I substitute u is equal to 0 and that t is equal to capital T. So what I will get if I do so? We get v equals to, in the place of u, 0. So you don't have to write anything here. Then g capital T. This is the velocity of the object when it hits the ground, final velocity. Take as equation number 6. The next step, I will get a second equation of motion, which is represented by this equation, equation 4. Is written as, what is equation number 4? Is this h equals to ut plus half gt square. On substituting the values, what are they? T is equal to 0, t is equal to capital T, and that's all. This is what we have to substitute. There's nothing else here. So we get h equals to 0 multiplied t is 0 multiplied t 0. There it is capital T. Because the place of t I write capital T, plus half g, then t square. So what I get? I get this. H equals to half g t square. That is the height of the object. Right? Now look at this carefully. What changes I am going to make to this? Now here, if you see, half is a numerical constant, and g is the acceleration due to gravity, which is nothing but 9.8 meter per square second near the surface of the earth. So it is also a constant. The whole term is a constant. Is a constant. Fine. So this equation can be written in this manner. H equals to a constant multiplied by t square from this equation. Then good here. A new thing I am going to tell you. Whenever we multiply constant with equal to sign, on combining these two, we get the proportionality. So h is directly proportional to t square. This is a new relation. This shows that when we increase the height, the time taken by the object to reach the ground will be more. Okay, with increase in height, the time taken by the object to reach the ground will increase. This is what it means. H is directly proportional to t square. See, when we increase the height, the time taken to reach the ground will increase. In a similar way, here, g is again a constant, isn't it? So, this can be written as v here equal to sign. G is a constant. T. I combine in the similar way. So, what I get? I get this. V is directly proportional to t. This shows that if you increase suppose the height is greater. No, when the object is dropped from a greater height, to reach the ground it takes more time. By then, if you check its final velocity when it reaches the ground, you may find that if it takes more time, the velocity of the object will be more. Okay, this shows that when time taken the object is more, this might have attained a more velocity. Now, this is applicable only for an object which moves only under the action of gravity. Clear? The next, I will find out the square of velocity with which the object has reached the ground when dropped from certain height using equation number 5. Square of velocity. Can be obtained using equation number 5. Equation 5. What is that? V square is equal to u square plus 2gh. Right? And here I'll substitute the value of substituting u equals to 0. What I'll get if I do so? I'll get this. V square is equals to 2gh. This is what I get. Again here, this two term, the constant. Right? So I got a new equation. V is equal to constant multiplied with height. So on combining these two, I get V square is directly proportional to h. This can be written as, on taking square root, V is directly proportional to root of h. No, that's it. No, what does it show? This clearly shows that velocity of the object will increase with the height. Therefore, increase the height, the final velocity with which it has reached the ground be a greater one. Okay, and before concluding this topic, let me provide one more equation which is obtained from this equation. Now I rewrite it. What I do, I keep a t one side, t is kept at one side. Now I taken this term to the left hand side and it is brought towards the other side. Now these terms are taken to another side. Here 2 is in the denominator. When it is taken to the another side, it will multiply. What I get? I get a 2h. Now g is in numerator. When it is taken to the other side, it will divide. This is how t square value is obtained. It is equal to 2h upon g. Now from this, if you take the square root, you will get the value of t to be equal to root of 2h upon g. Clear? Which in another way shows the same thing, that time taken by an object to reach the ground depends on the height at which it is placed. So this is how one can easily derive the equations of motion for an object under the motion of equations of motion of an object under gravity. And apart from this, I would like to tell you one thing. At the beginning, I told you about the free fall. What is free fall? When some object is dropped from certain height very close to the ground, only under the action of gravity, in the absence of air resistance, is referred as free fall. I repeat, moving of an object only under the influence of gravity is referred as free fall. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put your question in the comment section. Thanks for watching.